Sorry. Yes, students, we are going to talk about two types of satellites in this lesson. Uh, High flying and low flying satellites. There are certain satellites which are at very large distance from the center of the Earth. They have a certain speed in this orbit, they have certain kinetic energy in that orbit. We have expressions for this, and we have already learned how we calculate the orbital speed of any satellite moving in the orbit. So let me go back a step and remind you how we calculated, worked out that expression that we used to calculate the orbital speed. So first, the orbital speed. Whenever you want to calculate or work out the orbital speed, you want to derive the expression for orbital speed, you always start from gm m over r square, and I should write small r here, is equal to m v square over r. This is the gravitational force on any satellite which is orbiting the Earth. And this is the radius of the planet Earth. And this is the radius of the orbit in which the planet of mass m is moving with orbital speed v. So the total force, the net force that this planet is exerting on the satellite of mass m is this, and this force is playing the role of gravitational, the role of centripetal force. That is why we can equate this force to mv square over r. If I cancel this from the two sides, it's easy to see that v becomes equal to gm over r under root. This is the expression for the orbital speed in its simplest form. We can modify it according to the situation, depending upon what we are calculating, depending upon whether we are considering a high flying satellite or a low flying one. Let's see what is the typical value of the orbital speed for a high flying satellite, and for that I'm assuming that we are having a very far off satellite for which small r is equal to 3 times the radius of the Earth, which means if you are at the surface with this radius of the Earth, it is 3 times the radius of the Earth that the planet, that the satellite is moving. This is where the satellite is. So the total distance from the center of the Earth to the satellite is 3 times the radius of the Earth. Such a satellite will be considered a high flying satellite. So for high flying satellite, if I replace this r with 3 times the radius of Earth, this expression will be for a high flying satellite. V is gm over 3 times the radius of the Earth under. If we use all these values with this 6.67 into 10 to the minus 11 given in the data booklet, this value of mass of the Earth, which is usually given in the statement of the question, because you use it so often, you will ultimately remember this. This is 6 into 10 is for 24 kilograms. This is the mass of the Earth. And radius of Earth is again a standard value because we assume that Earth is spherical. So radius is always the same value more or less given in the statement of the question, and that is 6,400 kilometer approximately. So with all these values given, we can see that orbital speed of such a satellite that we term as high flying satellite will come out to be approximately 16,000 kilometer per hour, or nearly 4,500 meter per second. This is the situation when a satellite is very far away from the center of the Earth at a distance of 3 times the radius of the Earth. So for high-flying satellite, this is the orbital speed. How we calculate the kinetic energy, because that is also an important variable. We often calculate the energies of the satellites, sometimes kinetic energy alone, sometimes kinetic and potential energies are to be calculated, and then the total mechanical energy, and we later on learn how the potential energies are calculated. Calculating kinetic energy is easier because we know kinetic energy is equal to half mv square, the standard expression for kinetic energy. And if we replace this v with this orbital speed, this expression simplifies to g m over 2r. This is the expression for kinetic energy of any satellite which is of mass m, which is orbiting a planet of this mass in an orbit of radius r. So for all types of satellites, whether they are high satellites or low flying satellites, this is the standard expression. But of course, the values of the kinetic energies will become different for the high flying and low flying, and that is coming next, how that value changes when we consider a low flying satellite instead of high one. In order to qualify to become a low-flying satellite, the satellite should not be flying in a very large radius of the orbit. It should have a reasonably small distance from the center of the Earth. From the surface of the Earth, it is just a few kilometers away. So when I consider a low-flying satellite, I mean this is the planet Earth with such a large radius, and the satellite is moving in a radius which is slightly larger, which is only slightly larger than the radius of the Earth, which means this height h is so small that we can practically ignore it. It is negligible as compared to the radius of the Earth. So if I want to calculate the orbital speed for such a satellite, gm over r, under. There will be a change in this expression now, and that is gm over capital R plus h. And since this h is very small as compared to the radius of the Earth, this r plus h is nearly equal to the radius of the Earth. That means v, which is the orbital speed, becomes gm over capital R. So while here this small r was any radius larger than the Earth, larger than the radius of the Earth. It may have a very large value, 3 times the radius of the Earth, 2 times the radius of the Earth. But for this particular situation, when the satellite is termed as low-flying satellite, then this small r is replaced with capital R. And what is the significance of this? The significance of this is that this is the radius of the R now. This is a more definite value here now. And one more change that we expect is that this GM, we know already that G m over r square is equal to G. For all objects close to the surface of the Earth or on the surface of the Earth, this value, which we know as 9.81, this is equal to Gm over r square. If we equate this Gm to Gr square, our expression for V is changed further, and this becomes V is equal to G r square over r under root. We have replaced this Gm by this Gr square, and with this r is get cancelled, and this G r under root is the final expression for the orbital speed of those satellites which are low flying. If you remember, this is the same expression that we derived for the minimum speed required when an object was moving in a vertical circle, and in order to continue moving in the vertical circle without falling vertically down, this g times the radius of that orbit under root was the minimum value. So here again, the similarities, even though this is not considered a vertical circle and it is not horizontal, it is just a circular motion without any horizontal or vertical considerations. This V is equal to G times the radius of that planet, which is the planet under consideration, which in this case is the Earth. If I know this value 9.81, I know this value of the radius of the Earth, we can work out the value for this orbital speed, and in this case it becomes 8,000 meter per second, which was only 4,500 meter per second for the high flying satellite. So this is almost twice as large value. That means if an object was moving in a radius of orbit which was much larger value as compared to the radius of the Earth. This is for high flying satellite, and this is the low flying satellite. So this V was only 4,500 meter per second, and this, the low flying one, this is about 8,000 meter per second. So one thing is clear: when an object moving in a radius of larger value somehow moves into a smaller radius, its kinetic energy increases because its orbital speed increases. We can use the same expression for kinetic energy that we derived for the high-flying satellites in the case of that. The expression remains unchanged, at least for kinetic energies. The expression is the same, which we derived. That expression was 1/2 Gmm over r. This is the expression for kinetic energy. If I know the radius now, the radius is practically the radius of the Earth now. If I write it as the radius of the Earth now, the kinetic energy for the low flying satellites can be easily worked out. But kinetic energy is not the only type of energy that we have to worry about. At times, we are required to calculate the potential energies as well. But in the next lecture, we will calculate the potential energies of the satellites, and then we'll see what changes take place in the potential energy. Obviously, one thing which you will readily understand is that when an object moves from a much higher position to a lower position and its kinetic energy is increasing, its potential energy must go down. Its potential energy must decrease. So any decrease in the potential energy must correspond to an increase in its kinetic energy, and that is how the physics remains intact. The basic ideas of physics are applicable in this motion of satellite as well, but we'll talk about the potential energy and its variation in more detail in the next lecture.